Hello everyone, this is Dr. Young, and in this video I'm going to briefly show you how to determine if a compound is aromatic or not. Last time we talked about the importance of aromaticity. Aromatic compounds tend to be more stable and they react differently, so it's going to be important for us to know when something is aromatic and when it is not. Again, last time we talked about we have all these different nice smelling compounds, whether they smell like banana or lemons or limes or wintergreen or whatever. But that was sort of an original definition of like, oh, look, all these compounds have a smell. Now, not all of these are actually quote unquote aromatic compounds. Last video, I said that only these three are actually considered to be aromatic. The last two are not aromatic. One doesn't even have a ring, and they certainly don't have a full system of conjugated pi bonds. So what we're going to do in this video is we're going to take a closer look at, well, what does it mean to say, what am I talking about when I say a full ring of p orbitals? And why is it important that it's planar? And what is Huckel's rule? And what's this 4n plus 2 business? Okay, so let's take a closer look. Now we're going to go through these one by one with all 6 of these compounds here to determine if these are aromatic, anti-aromatic, or non-aromatic. Non-aromatic means it fails one of these first two. So I'll just write that down real quick. Let me do it here. So the term non-aromatic is honestly most things. Non-aromatic means it just fails 1 or 2. So either you don't have a 4 ring of p orbitals or you're not planar. If you hear the term anti-aromatic, 1 is good, 2 is good, but the problem is that with regards to part 3 here, the following the Huckel's rule, if you have 4n pi electrons, that's when you'd be anti-aromatic. So not 4n plus 2, but just 4n pi electrons. So if you have 4 or 8 or 12 electrons, something like that, then you'd be considered anti-aromatic if you were still had a 4 ring of p orbitals and planar. So let's take a closer look. 4 ring of p orbitals, what I really mean by that, the most important thing is that we don't have any sp3 hybridized carbons or hydrogens or nitrogens or whatever, not sp3 hydrogens, carbons or nitrogens or sulfurs or oxygens. So if I take a look at benzene, right, which we should know is already aromatic, it's what I've been talking about in the previous video. But if I look at any one of these given carbons, right, they're all sp2 hybridized. They all have 3 areas of electron density: the carbon to the left, the carbon to the right, and the hydrogen that they're attached to. So they're all sp2. Which means they all have a p orbital left over, right? If you've hybridized 2 of your 3 p orbitals, that means you still have 1 p orbital left over. So benzene definitely follows the full ring of p orbitals. Yes, it has a full ring. So I'll say for number 1, yes, it does have a full ring of p orbitals. Now, if we look at the compound right next to it, I certainly do have carbons that are sp2 hybridized. However, I have one that's sp3 hybridized, which means there is no p orbital here, so I cannot have that conjugated system. I cannot delocalize my electrons around in a ring like I could with the benzene. So right off the bat, I know that this second compound is not aromatic. Specifically, it's non-aromatic, but it is just not aromatic. So I'll say not aromatic. And I'll come back to the first one here. I'll come back to benzene, and we're just going to go through each one of these criteria one at a time. So not aromatic. Now this one, oh sorry, I don't know why I put 2 there. Just kidding. We're still on number 1. So now if I look at the next compound, this is a furan. Same idea. Okay, well, you know, this looks like it's sp2, that looks like it's sp2, sort of the other ones in the alkenes. So what do I think about this oxygen? Is that sp2 or sp3? And now at first glance, and you may have heard me talk about this before if you had me for, if you've had me for Oakham for a long time. At first glance, it looks sp3, right? At first glance, it looks like I have an area of electron density around 1 lone pair and another lone pair and 1 single bond and another single bond. So it looks sp3. And you notice that I'm being all dodgy about this. It is not actually sp3. Because if we take a closer look here at this compound, right, this lone pair on the oxygen can be delocalized, right? It's a lone pair on an atom, and it is next to something that has a p orbital, so we can draw resonance structures. And if you take a closer look at that resonance structure, I'm going to get something like this. I'm going to get something like this for my resonance structure. And now if I look at that oxygen, I only see that there's 1, 2, 3 areas of electron density around it. I have a lone pair, where the pi bond is, the double bond, and then the single bond. So really, this oxygen is actually sp2 hybridized. Or in other words, I do have a 4 ring of p orbitals. Everything there is sp2 hybridized. It's not really sp3. Right, and another way we can prove this to ourselves, right, is if a lone pair, let's look down here. I have a pi bond here. I have 2 electrons in a pi bond in this resonance contributor. We know, right, from Gen Chem and early OChem that anytime you have a pi bond, those electrons are from p orbitals. So if this oxygen is participating in any amount in a pi bond, it must have electrons in a p orbital, which again implies that it must be sp2 so that I can have that leftover p. So this oxygen here, right, either way I draw it, really it's more sp2-like. Or in other words, that lone pair can drop down and participate in all these resonance structures. Sorry, I just realized that I forgot the double bond that was still in that ring. So I would say yes. Yes, this compound has a full ring of p orbitals. Everything has at least 1 p orbital, right? Or in this case, everything is sp2 hybridized. If I look at the next one, same kind of weirdish question. It's kind of a weird looking compound. This is azoborane because it's azo for nitrogen and borane for the boron. All the alkenes clearly sp2. This boron, it only has 1, 2, 3 areas of electron density, so that definitely looks sp2. And then I have a nitrogen, which again looks sp3, but just like with the example before, I can have this lone pair drop down and join the pi system, so that nitrogen must also be sp2 hybridized. And so for this one, I also am going to say, yes, it has a full ring of p orbitals. Looking over at the one with the carbocation, again, yes, right, those are sp2 hybridized. Now the carbocation, right, keep in mind that there is something still here. There is only one H where this carbocation is. And remember that our carbocations are in fact sp2. If you go back to remember either anything from additions to alkenes or the SN1 reaction, the carbocation is sp2 hybridized. It's trigonal planar, it's flat. So this also would have a full ring of p orbitals, as would this last one. So really the only compound up here that we have is the first one. That's the only one that did not have a full ring of p orbitals because it specifically had 1 carbon that was sp3 hybridized. The oxygen, the nitrogen here are actually sp2 because their lone pairs drop down into the pi system. So everything has 4 rings of p orbitals except for the second one. So let's look at the planar part, right? So is it planar? And that just means it needs to pretty much be less than 8 carbon. So 7 carbon ring would be okay, 4 carbon, 3 carbon, 6 carbon. Those would all be okay sizes, right? It just needs to be planar, it needs to be flat. And the reason it needs to be flat is so all of those orbitals can line up, right? If you remember with the benzene, I showed you in that previous video, if you take a look at benzene, right, we said that all of the p orbitals on benzene need to be able to overlap. And so the benzene needs to be flat. Benzene is super flat. It's not like a chair conformation or anything like a cyclohexane would be. They all need to line up so that you can have that good overlap for all of the lobes on top of the benzene and all of the lobes on the bottom of the benzene. If this is all wonky and it's all twisted up, then it's not going to be flat and these p orbitals can't line up and overlap well. And so you don't get that nice conjugated pi system. So basically, once you get to 8, you start to buckle and start to look funny. And I'll draw a picture of that in the next one. So for the benzene, is it less than 8? Yes, it is. So that must be planar. I'm going to skip the second one because I don't care anymore. It doesn't have a full ring of p orbitals. Here we have a 5-membered ring, so that's a yes. Another a 6-membered ring, so that's a yes. And then a 5 and a 3. So all of these are smaller than 8, so they're all going to be planar. That all sounds good. They're all good. They all can have planarity. And again, that's so that all the p orbitals can line up. And then the last thing, which is where I think students have the most trouble, is following this Huckel's rule, right? So it's saying that you have to have 4n plus 2 electrons. And all that's saying is that n is just any number 0 to infinity. And then you plug it into this 4n plus 2 thing to spit out an okay number of electrons, right? So here's where your n, and here's your number of pi, specifically pi electrons. So when n equals 0, and again, this doesn't really correspond to anything on the structure. This is just spitting out a random, well, what if it's 0? What if it's 1? What if it's 2? What if it's 3? What if it's 4? And then on to infinity. Now, we don't really care about going up to infinity because our molecules are small. But the idea here is that, well, when n equals 0 and you plug this in, 4 times 0 is 0 plus 2. So when you put this into this equation, you just get 2, right? 4 times 0 plus 2 is 2. When n equals 1, you get 4 times 1 plus 2, that equals 6. When n equals 2, you get 8 plus 2 is 10. When n equals 3, you get 12 plus 2 is 14, 16, 18, and then 20, 22. And then you just keep on going on and on and on and on and on. So what we're saying is that the allowable number of electrons in a pi system to make something aromatic is 2 or 6 or 10 or 14 or 18 or 22. And note that this is just the pi electrons. So if I go to my benzene, which again we know is aromatic, but we're just applying these rules here. If I go to benzene, I look at just the pi electrons. I'm talking about the electrons in the pi bonds, the ones that would be moving around when I draw a resonance structure, right? Those would be the ones that I'd be moving when I draw a resonance structure, right? I'd move those there, and then move those there, and move those there. And if you look at those, for every pi bond, right, there's 2. So I've got 2, 4, 6. I've got 6 pi electrons in this system. Does that follow Huckel's rule? Sure enough, it does, right? There's 6. 6 is an allowable number. It fits into the 4n plus 2 thing. So yes, benzene is aromatic, right? We already knew that, but according to these rules, it follows these rules too. I'm going to skip the second one because I don't care because it doesn't have a 4 ring of p orbitals. If I go to the third one, same thing. I want to know how many electrons am I moving around when I do these resonance contributors, when I draw these resonance contributors, right? How many electrons are delocalized through the pi system? And so I would definitely start off with my pi bonds, right? 1, 2, 3, 4. And then the question is what to do about the oxygen's lone pairs. Do I not count any of them? Do I only count 2 of the 4? Do I count all 4 of the electrons in those 2 lone pairs? And so what we do is we just are counting the ones that move when we do the resonance structures, right? So I only moved these 2 here. I didn't touch the other ones. Those 2 that I just circled in purple, that I just highlighted in purple, those are the ones that do move. So altogether I have 1, 2, 3, 4, 5, 6 pi electrons again, which means this also is aromatic. Yes, this is aromatic. Let me, instead of writing yes, I'm going to write if it's aromatic or anti-aromatic. Just so we get to apply these terms. So no, the first one is aromatic. The third one is aromatic. Let's look at the fourth one. Same question, how many electrons are moving around this pi system? It's actually really similar to the one before. I've got the 2 and now 4 from the alkenes, and then I move 2 electrons from the nitrogen. Those are the only 2 that it has, but I do move them when I draw the resonance structures. So once again, we have 6 pi electrons. So once again, this is also an aromatic compound. If I move to my, fifth one, my fifth one here with the carbocation and the 5-membered ring, same thing, counting up my electrons, I've got 1, 2, 3, 4, but that's all I've got, right? The carbocation doesn't have any electrons on it, it's just empty. So I only have 4 pi electrons, which is not on my list of allowable numbers of electrons from the Huckel's rule, right? It goes 2 and then it goes to 6. 4 is not one of these. And in fact, 4 follows the 4n thing, where I was talking about being anti-aromatic. So this would actually be an anti-aromatic compound, where it has electrons in orbitals that are not going to help stabilize it. So this would be anti-aromatic. Versus the last one, I only have 1 pi bond, so I only have 2 pi electrons, which is allowable, right? I can have 2. So this last one would be aromatic. So here's how we apply those rules, right? First, you're going to look for, do I have a 4 ring of p orbitals? Or in other words, nothing is sp3 hybridized. And then I'm going to make sure that they're all less than 8, so they're all nice and flat. And then I'm going to follow Huckel's rule, which is just saying that the number of pi electrons needs to equal 2 or 6 or 10 or 14. We're not really going to see anything beyond that, but in theory, it could go up to infinity. So let's apply this to a couple more examples. So you should take a look at these. I'll pause for a sec. Why don't you pause the video, see if you can figure out if these things are aromatic or not. So if we're looking at the first one here, right off the bat, 4-ring of p orbitals. It is a cyclohexane shape, but I don't see any double bonds, right? All of these carbons are sp3 hybridized. So it does not have any, it doesn't have any p orbitals, actually. So this is just not aromatic. It's a non-aromatic. Just a normal compound. It's not aromatic at all. I don't even need to worry about is it planar or follow Huckel's rule, because I don't even get past that first criteria. For this second one with the nitrogen, this is a pyridine. This is pyridine. Do I have a 4-ring of p orbitals? Yes. Every single thing in here is sp2 hybridized. The lone pair on this nitrogen doesn't drop down. If you try to do that, you'll see there's some really funny structures. You'll get something that looks sp that wants to be linear, that's bent into this weird ring shape. That lone pair does not. That lone pair does not participate in the pi system. In fact, let me draw this as a side view for you, so you can kind of help visualize that. The lone pair is not in the right place. So here's the nitrogen. Again, this sort of shaded front part is supposed to mean that, this, it's like laying flat, but this dark part is kind of coming out at us. And so what we're saying here is we've got a double bond here, double bond here, double bond here. That if you look at the pi system, right, I'm saying that this is sp2 also. If you look at the pi system, we've got one up, one down there, one up, one down there, right, just like benzene. And since this nitrogen is in a double bond already, right, we can clearly see the double bond. It's double bonded to a carbon on its right on my upper picture here. So all of those p orbitals are all lined up nice, right? I can have all that nice overlap on the top and on the bottom. But what that means is, since the nitrogen is sp2 hybridized, what that means then is that lone pair is actually sticking out in an sp2 orbital, right? These were all the p orbitals. And that's perpendicular to, right? This is 90 degrees. It's perpendicular to where all of those p orbitals are. So it's sticking out way in the wrong direction. It's sticking out in the same plane as the whole flat ring is, whereas the p orbitals are on top and on the bottom. So that lone pair is in a totally wrong place. So it is not participating in that pi system. So it does not count. And that'll be important in a second. It's not going to count for my Huckel's rule. But this does have a 4-ring of p orbitals. Does my big cyclooctane thing have a 4-ring of SPs? Yes, it does. Everything in there is sp2 hybridized. Everything has p orbitals. And then lastly, my little guy down here, yes, my cyclobutadiene also has all sp2 hybridized carbons. So then I look at part 2, the planarity. Again, I don't care about the first one. It doesn't even have a ring of p orbitals. Number 2, is it less than 8? Yes, it is less than 8. Number 3, is it less than 8? No, it is not less than 8. It is too big. It is 8. And what this means, the problem with this is that because it's so big, in order to like reduce angle strain, let's see if I can draw this, it ends up kind of buckling a little bit so that you get this weird sort of almost boat-like shape. And the problem with that is that it then gives you p orbitals that are lined up funny. And I won't draw them all because it's going to get really ugly really fast. But like there's one pi bond and it's overlapping p orbitals. But then you go down here and here's a pi bond and it's overlapping p orbitals. Notice how they are not in any way, shape, or form all nice and lined up like we saw over here on the left with the pyridine, right? These are all in the same plane, all straight up, straight down. Here, because it buckles, because it gets so big, it bends them out of place, and they're no longer able to overlap, which means they don't have that extended pi system, which means the electrons are not as delocalized as they would be in something that was flat. And so the p orbitals, these pi bonds here, they don't really interact with each other as much as they would if they were planar. And so because this is not planar, it is not aromatic. I don't get that extra stabilization from the delocalization of those pi electrons. And then so if I look at my very last one here, Yes, that is less than 8. Yes, that would be planar. And then to go through these, so I really just am looking at the first and the third one now, or sorry, the second and the fourth one. How many pi electrons do we have? Well, I've got 1, 2, 3, 4, 5, 6 from the pi electrons, and we just said that these are out of plane. Right, they're out of the plane where the p electrons, sorry, the p electrons, the p orbitals, the pi electrons are. It's out of plane, so that I don't have to count those. I do not count those. So that means I just have 6 pi electrons, which we said was a good number. So this would be aromatic. So pyridine is an aromatic compound. It is surprisingly stable, and it does do all of these electrophilic aromatic substitutions that we're about to learn about, this new reaction type. I'm just going to skip the big cyclooctane thing, tetraene, because it's not planar, so I don't have to worry about it. And I'll jump right to this cyclobutadiene. It looks like I have 1, 2, 3, 4. I've got 4 pi electrons, which, like we said before, that's not the right number, right? That doesn't follow the Huckel's rule, the 4n plus 2 rule. It follows a 4n rule, so this is actually anti-aromatic, which means it is less stable and more reactive. It really wants to do something with all of its electrons. It has weird unpaired electrons, pi electrons, in its molecular orbitals. So anyways, I hope this gives you a good idea of how to determine if something's aromatic or not. You'll want to have this skill and be like, that's aromatic, that's not, especially in the context of being able to identify what types of reactions or what types of reagents you need to add to a compound in order to get it to add whatever thing you want, whether it's a bromine or an alkyl group or what have you. So anyways, happy studying, good luck, and watch the next video.